Hello everyone, today I want to build a cut knurling tool. This kind of knurling tool is a bit obscure in the hobby machining sphere. There are some videos about people making and trying these, but from looking at how they designed their tools, not all of them understand entirely what is involved with cut knurling. So first of all I'm going to walk you through the mechanics of cut knurling, how to design a single roller tool and how to use one, and after that I'll show you the build. The fundamental difference between form knurling and cut knurling is the forming action versus cutting action. The form knurl presses the pattern into the surface under high pressure, while the cut knurl has a sideways cutting action which forms chips and removes material to shape the knurled surface. This means the knurling wheels are different from each other. Generally, the form knurling wheels have a chamfered edge, while the cut knurling wheels should be dead sharp. The difference has some implications to usability. Form knurling has greater radial tool pressure and will have difficulty knurling parts consistently with a high length to diameter ratio, whereas cut knurling has lower tool pressure and allows more freedom in the setup of your part. On the other hand, form knurling rolls are widely available and the holders can be very easily made. Cut knurling tools are a little bit more involved to design, so let's dive into how those work. The cutting action in a cut knurling wheel is created by holding the wheel at an angle relative to the work. When the wheel makes contact with the work, the surface speed of the work is imparted onto the wheel. However, because the wheel is canted at an angle, a sideways surface speed is also created. From the point of view of the work, the teeth on the wheel are shaving the pattern sideways into the work. This is true for straight knurling as well as diamond pattern knurling. Because the surface speed of the work is split into two speeds on the wheel relative to the work, friction is also generated. For this reason, and also generally to improve cutting and to flush away shavings, cut knurling should always be done with a flood of oil or coolant. Now let's take a look at how a cut knurling wheel needs to be positioned relative to the work to achieve this cutting action. The wheel needs to contact the work at center height in the lathe. This will make sure the presentation angle between the work and the wheel is the same at all diameters. Now remember that the wheel contacts the work at the edge of the wheel, not in the middle. So half of the wheel thickness has to be taken into account when designing the head. In my case, I made the head able to index around an axis. The wheel edge apex is positioned exactly in line with this axis. This means I can flip the head and cut in reverse as well without changing the center height. This axis runs exactly down the center of the 25mm tool shank, which I can set up into a preset tool holder block and be confident that everything will line up as I intended. The cut knurl wheel does not need any other additional clearance or adjustment in angle. If the head were to be mounted horizontally, it would function exactly the same as a form knurl wheel. Do not position the wheel with a back clearance angle. The fact that the wheel itself is angled for cutting automatically creates back clearance. With this information, you should be able to easily design your own single roller cut knurling tool. I mention this because in industry there are also double roller cut knurling tools. These are much more complicated because the axis of the wheels needs to be adjusted to the workpiece diameter, and one of the wheels cuts on the front while the other cuts on the back. It's a deep subject that's generally not worth pursuing for a hobbyist. With a single roller tool, we just make 2 passes instead of 1 to knurl diamonds. That is to say, if you have hundreds of parts to be knurled and you want to do them in 1 pass, look into investing into an industrial CNC double roller cut knurling head. To use the cut knurling tool, we need to keep some things in mind. These tools need to be fed in radially at the start of the workpiece, 1 to 2 pitch lengths into the work. And after that the tool can be fed axially along the part. A cut knurl tool cannot knurl to the end into a shoulder. The depth of cut on diameter on a cut knurl wheel is equal to the pitch of the teeth on the wheel. The feed rate for cut knurling can vary based on material, but 0.1 mm per rev is a good starting point. The starting circumference of a knurled surface being divisible by the pitch of the knurling wheel is debatable. It's best to try on a scrap piece of the same diameter before committing to knurl a final piece. The company AccuTrack has a very helpful article on the use of cut knurling tools. I will link it in the description. To build a cut knurling tool, the only special parts that I needed were the cut knurl wheels themselves. Be careful, they are different from the form knurl wheels. They tend to be more expensive because the teeth are very finely finished and the faces are dead sharp. Some notable manufacturers are Quick, Zeus, Dorian and AccuTrack. They are for sale on AliExpress as well, but they are still surprisingly expensive there. With the head canted at 30 degrees you can make straight knurling, 30 degree diamond knurling and 45 degree diamond knurling. Straight knurling happens with a 30 degree angled wheel, 30 degree diamond knurling happens with a straight knurling wheel, forward for the right hand spirals, reverse and flip the head for the left hand spirals. For the 45 degree diamond knurls you will need two 15 degree wheels because 30 plus 15 equals 45. Left and right hand wheels and go forward and reverse as well. Let's cut a test part to demonstrate. I have prepared a bar of mild steel and I've calculated a diameter that is divisible by the pitch of the knurling wheel. I'm going to cut a 30 degree diamond pattern over the turned diameter. The first pass I will make in the forward direction, that means the cutting face of the knurling wheel has to point 30 degrees upwards. The material to be cut always has to move into the face of the wheel, not into the circumference. I've set a slow RPM and a feed of 0.1 mm per rev and we will be cutting without tailstock support. It looks like the left-hand spirals have cut deeper than the right-hand spirals. I may have underestimated the tool pressure this knurling tool imparts. It's worth mentioning that the second pass only cuts half the material of the first pass. I will run the right-hand pass again to the same depth value and see if I can get the cut depth to match the left-hand pass. After taking a spring pass, the left and right hand spirals look like they have the same depth. For a quick and dirty test cut, this looks pretty good. Notice how the tips of the knurled pyramids end almost in a sharp point. With a little trial and error, I'm pretty sure I will be able to cut crisp and completely sharp knurling. From here out, I'll be showing the build of the knurling tool. I'm starting with rough sawn blocks and first I need to square them up and mill them to size. While squaring up the blocks, I was having issues with the surface finish. I know that normally this tool can cut a very nice surface in steel. After changing the inserts, the surface finish dramatically improved. The inserts likely had some built-up material on the tip and were scratching the surface. A built-up edge can be related to not enough surface speed. I find that on the mill sometimes I still walk into surprises in terms of my parts not being the size I intended. So this time I paid special attention to use a system to reach my dimensions. I used the same parallels for all surfaces, hammered down the parts down in the vise, used the DRO zeroed on the parallels to get different dimensions, and took light finishing passes to reach final size. Spot drilling for the 10.5mm through hole. This is a deep hole and I want it to run relatively straight through the part because the exit position needs to be in the right place. Spotting will ensure the drill starts straight and lessens the chance of the drill going off course inside the material. Drilling at slow speed, relatively high pressure, and WD-40 as lubricant. The WD-40 easily seeps down to the bottom of the hole, even while drilling to lubricate the cut. With normal cutting oil, probably not much would reach the bottom of the hole, but most would be ejected with the chips instead. Counterboring for an M10 socket head cap screw. I have two sets of these counterboring bits from AliExpress and I have to say they work surprisingly well. I've used them in many projects and not one has yet dulled or broken. That being said, I always run them slow and with a lot of oil. Countersinking the edges. I also like to break the inside edge where the bolt head sits. Often the radius interferes if the corner is left sharp and result in a not fully supported bolt which can be unstable. I flipped the part around and now I'm counterboring to a different size to accept the drill bushing. I am applying a mounting paste to press in the drill bushing. The bushing will serve to align the knurl head on the correct center height and will allow the bolt to pass through the middle. The quill of the milling machine is enough to press the bushing into place. It was only a light press fit. Drilling the index pin holes. I'm taking great care in positioning the holes because the head is designed to be located with two tight-fitting pins. If the position is off by too much, the head will not fit on the body. To try and ensure correct position, I'm first pilot drilling with a carbide drill, then spot drilling, pre-drilling for a reamer, and then reaming with a carbide reamer. I have two types of pins in this nominal size, so let's try which one fits. First is a roller from a needle bearing, which fits nice. The other is a dowel pin which doesn't fit by hand. It's a dowel pin with a tolerance for a press fit. I'll use the bearing needle. spotting, drilling and tapping M10 so the bolt can clamp the head to the shank of the tool. Boring out part of the thread so the drill bushing fits in it nicely to position the head accurately. Spotting, drilling and reaming the index holes in the head. These holes will position the head either plus or minus 30 degrees by registering with the pin installed into the tool shank. Test fitting the shank onto the head. This tells me if I drilled and reamed the pinholes correctly. Everything fits together nice and tight. Tapping the hole where the wheel assembly will be mounted. I'm power tapping first, but finishing by hand because the thread needs to go all the way to the bottom. Not the best way to design things, but for a one-off tool it can be done. counterboring to make place to mount the wheel axle. Catering to the chamfer enjoyers with the following few shots, some large chamfers coming up. Big mistake here. Wound the handle the wrong way and destroyed one side of this chamfer intersection. I'll have to live with that for the rest of my life. Yep, everything still fits. Now off to the lathe to make parts for the wheel assembly. I'm using 42 chromo 4 steel, aka 4140, because I want to heat treat these parts to make them wear resistant. Drilling the through hole for the screw. This will be the countersunk top washer, hence the large chamfers. I wasn't happy with the finish, so I tried again with slower speed and oil. Hardening the parts. Notice the larger part is not as hot as the smaller one. It turns out it was not hot enough to fully harden. I should have used my oxypropane torch to heat these. Either way, the part works. Maybe in the future I will get around to making one that's properly hardened. Facing the washer with the CBN tool I brazed in the previous video. The part is mounted in a collet block in the through jaw chuck. Here I forgot to reverse the direction of the spindle and chipped my CBN tool. I didn't notice it at the time, and surprisingly the tool kept on cutting nicely. Checking size with a micrometer. This fit is very important because I want to leave enough room for oil, but not too much or it gets sloppy. The micrometer is preset to the exact size I want to leave the correct gap, so I just have to turn until it reads 0. Three microns over size, that will do nicely. What I'm doing here is turning the step height to the exact length to capture the wheel, but again to leave 0.02 mm clearance on each side of the wheel for oil. The indicator measures the movement of the carriage directly, since I don't have a DRO on this machine. The wheel is exactly 5 mm wide and the step will be 5.04 mm. Since the top washer is flat, this will be the running clearance for the wheel. Test fitting the wheel assembly. Okay, one more test cut. This is in 42 Chromo 4 or 4140. These wheels from Quick are made from a special steel that is advertised to be able to cut high tensile materials as well. Looks good to me. If you decide to build one of your own, let me know how it goes.